So now that we've talked about the fact that acids and bases can be strong or weak, and we know from previous chapters when we have things that go to completion versus things that reach an equilibrium, that impacts the amount of product we're able to form. In the case of our acids and bases, that's going to impact the amount of hydronium or hydroxide, which is going to impact our pHs. So here we'll take a look at how we would go about determining pHs of strong versus weak substances. So when we talk about our strong acids and bases, pHs for these is determined very differently from weak. In order to do any calculations in this chapter, we've got to first start off by identifying our substance as an acid or a base. Then we have to determine, is it strong or weak? And the way we do this is we have got to know our strong acids and bases. So remember our strong acids, we had 6 and only 6. So hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric acids. And then our bases were group 1 or 2A hydroxides. And if we have an acid or base that doesn't fit into these, then it's weak. So when it comes to our strong acids, remember that we've got water. Water outer ionizes. It's producing hydronium and hydroxide. But remember, our concentrations are 1 times 10 to the negative 7th. That's going to be a negligible amount compared to what an acid or base will produce when we put them into water. So essentially, what we can assume for a strong acid is that our hydronium concentration equals the concentration of our acid. A strong acid is going to completely dissociate, so all of the hydrogens become hydronium. So if we had something like HCl in water, and we start off with a 2 molar solution, all of these hydrogens off of that chloride or the hydrogen chloride are going to become hydronium. And so everything's going to be in a 1-to-1 ratio. So we would produce 2 molar hydronium and 2 molar chloride. And so therefore the concentration of our acid equals the concentration of our hydronium. So that means for a strong acid, pH is straightforward. We're just going to take the negative log of our acid concentration. When it comes to our bases can be a little bit more complicated. The concentration of the base is not necessarily the hydroxide concentration. It depends on the compound formula and the number of hydroxides in the formula. So our strong bases are either a group 1A hydroxide, so that we would have whatever that group 1A cation is attached to 1 hydroxide. So when that dissociates, for every 1 mole of compound we have, we've got 1 hydroxide, so we get 1 mole of hydroxide. The other possibility is we could have a group 2A cation, which is going to have the formula MOH2. So for every 1 molecule of that compound, we're actually producing 2 hydroxides. And that's going to impact our concentration. So we'll look at some examples of calculating both the strong acid and strong base pH. So as we said, it's very, very good to get into this habit in this chapter of identifying, do you have an acid or a base? Is it strong or weak? So here we've got a solution of 1.25 times 10 to the negative 3rd molar HNO3. And so we're asked, is this an acid or a base? So remember our acids, we look for hydrogens out front, we look for COOH or positive. And I have a hydrogen out front. This is going to be an acid. So then we're asked, is it strong or weak? So remember, we've got our list of 6 strong acids. We run through that list. HNO3, nitric acid, is one of them, so it is strong. So again, we know it's strong because it's one of our 6 strong acids. So since it's a strong acid, our pH is the negative log of that nitric acid concentration. And so we would get a pH of 2.903. So again, remember talking about our significant figures. My concentration here, 1.25, has 3 significant figures. Remember, when we take logs of things, our significant figures show up in the decimal places only. So I need to make sure that I reflect my 3 significant figures by having 3 decimal places. Now next we're given a solution of 5.67 times 10 to the negative third molar strontium hydroxide. And we are asked if this solution is an acid or a base. So again, running through my acids, I look for hydrogens out front, which I don't see. I look for COOH, which I don't see. I look for positive, I don't see. So running through my bases. Bases have hydroxides or nitrogens or negatives, and I have a hydroxide here. So this is a base. So then we identify it as being strong or weak. So remember, to be a strong base, so group 1 or 2A hydroxide, and weak will be all others. Strontium here is group 2A. So this is a strong base. Now, since we have a strong base, we have to account for the number of hydroxides. So the base concentration is not automatically my hydroxide concentration. So I cannot just go take the negative log of this like we did with our acid. So I'm going to go ahead and write the equation for the dissociation of this base. So if I take strontium hydroxide and I put it into water, it's going to dissociate into strontium cations. And that subscript of 2 here means I'm getting 2 hydroxides. So when this dissociates, it's a 1:1:2 ratio. So if I start with 5.670 times 10 to the negative third molar of my base, I'm going to produce 5.670 times 10 to the negative third molar of my strontium, and I'm producing twice that for my hydroxide. And so that's going to make my hydroxide concentration 0.01134. So if I have my hydroxide concentration, I could calculate my POH. So my POH is the negative log of the hydroxide concentration. So my POH is going to be 1.9454. I had 4 significant figures in my concentration. I need 4 decimal places to represent my 4 significant figures. My pH is going to be 14 minus my POH. So my pH will be 12.0546. So if I'm dealing with a strong substance, their pHs are fairly straightforward. If it's an acid, we're just taking the negative log of the acid concentration. If it's a base, we've got to pay attention to our subscript. So we would multiply our concentration by whatever subscript we have on the hydroxide. That gives us the hydroxide concentration. And from there, depending on what we're looking for, we can get our POH and then our pH. Now, when we deal with weak substances, it's a bit more complicated due to their reversible nature and the fact that they're going to reach an equilibrium. Calculating pH requires recognizing when we have weak acids and bases versus when we have strong. If I've got a weak acid, so these are going to, again, typically begin with an H plus or end with a COOH, and they're not one of my 6 strong acids. Our weak bases are going to usually be amines or ammonia derivatives, in which we have one or more hydrogen replaced by carbon groups. Because weak acids and bases undergo partial dissociation, they reach equilibrium. And with equilibrium, we're going to see the same types of calculations that we did in our previous chapter. So we can use equilibrium concentrations to calculate equilibrium constants, or we can use equilibrium constants to calculate equilibrium concentrations. When it comes to pH, pH depends on the equilibrium concentration of hydronium. And so we're going to be looking at using Ka, so remember that's our acid dissociation constant. We're going to look at using Kas to determine pH. Now, from our previous chapter, chapter 14, remember that equilibrium concentrations are determined from ice tables. Problem number 2 on our worksheet. We've got a 0.25 molar solution of HC4H7O2. Now, ultimately, we're going to be looking for the pH of this solution. But our worksheet's going to go ahead and break it down for us into individual steps. So with any problem we approach, we want to identify, do we have an acid or a base? Is it strong or weak? So looking here, I have a hydrogen out front. That lets me know I have an acid. So then we determine, is it strong or weak? I have my list of 6 strong acids. I run through that list. This is not part of those 6 strong acids. And so it is a weak acid. So we want to write our equation for the dissociation or proton transfer here. So I'm going to start with my acid. I'm going to show it interacting with water. It's weak, so we're using our double arrows indicating equilibrium. As an acid, it's going to donate that hydrogen to the water molecule, producing hydronium. And our conjugate base of C4H7O2. Now, it's an equilibrium, and we talked earlier with our weak acids that their equilibrium is represented by an equilibrium constant, just like any other equilibrium constant or equilibrium reaction. And for the case of an acid, that K is going to be referred to as a Ka. So we can set up our expression. Ka equals the concentration of hydronium times the concentration of our C4H7O2 minus divided by my original acid. Again, remember water is a pure liquid, which we omit from our K expression. We're being asked to set up an ice table in order to determine the concentrations of all materials present at equilibrium. And so we're going to set this up just like we would problems in previous chapters. So we've got our reaction here. Below it, we're going to set up our rows labeled I, C, and E. And we're going to plug in any information we're given in the problem. And the only thing we know right now is the initial concentration of our acid. So our acid is 0.25 molar. Water, it doesn't really matter because that water is a pure liquid. It doesn't appear in our K expression. It doesn't matter how much we have. And remember, for any of our reactions, we're going to assume our products are 0 unless we're told otherwise. So we're looking for equilibrium concentrations, and we have a K value. So we're going to set up the rest of our ice table in terms of X. So my acid is going to go down by X. My products are going to go up by X. Just like we did in previous equilibrium problems, we take our equilibrium line and we're going to plug it into our K expression. So I have X for hydronium and X for my conjugate base. So X times X will give me X squared divided by my acid concentration, which is 0.25 minus X. And that equals our K of 1.5 times 10 to the negative fifth. Now, when we looked at equilibrium before, when we got to this point, we said that there were a couple of things that we could look for. So we looked to see, do we have perfect squares? I don't have perfect squares here because I only have a square on top. I have an x squared and an x, which means I have a polynomial. But if we can avoid using that quadratic equation and rearranging this, then we generally want to. And so what we're going to talk about briefly is one more way that we can solve problems once we get to this point. So we're dealing with weak substances now. Notice that my K is a small k. When K is small, remember what that means conceptually. It means that our equilibrium favors the reactants. We're going to use very little of those reactants. We're going to form very little product. When K is small, it's a possibility that X might be negligible. When we say X is negligible, it doesn't mean it doesn't have a value. It just means that it's so small that when we add or subtract it, it doesn't significantly change the value. And so we're going to check to see if X is negligible. And the way we do that is we're going to compare our equilibrium constant to our initial concentration. So we're going to take K and divide it by I. If it is less than or equal to 10 to the negative third, X will be negligible. So my K is 1.5 times 10 to the negative fifth. My initial concentration is 0.25. This is going to give me a value of 6 times 10 to the negative fifth, which is definitely less than 10 to the negative third. So my X is negligible. Now, what that means is that if X is negligible, we can drop any plus X or minus X from my equation. So here I've got a minus X. This means we can drop that. And if I drop that, my equation becomes X squared over 0.250 equals 1.5 times 10 to the negative fifth. Now I don't have a polynomial. I have something much simpler that I can just rearrange and solve for my X. So in rearranging this, we're dividing by 0.25. We want to get rid of the bottom of that fraction. So we're multiplying both sides by 0.25. And then we're going to take the square root of both sides. So my X is going to be 1.9 times 10 to the negative third. So just like any other equilibrium problem, we're now going to take our X value and we're going to go back and we're going to plug it into our ice table. So that means that at equilibrium, I am going to have 1.9 times 10 to the negative third molar of my conjugate base. I'm going to have 1.9 times 10 to the negative third molar of my hydronium. And then if I subtract 1.9 times 10 to the negative third from my original concentration, that is going to leave me with 0.248 molar. So again, my X had a value. It's just that X is small. When I subtract it from my initial concentration, we get a very minimal change. So now at this point, we have concentrations at equilibrium. So ultimately our goal is to calculate the pH of this solution. We can't do that until we have these concentrations. So many times when you encounter these problems, it's not going to tell you to do all these individual steps. It's going to give you the acid concentration, and it's just going to ask you for the pH. These are the steps you have to take to get there. You've got to figure out, do you have an acid or a base? Is it strong or weak? You have to have your proton transfer equation, set up an ice table, and solve to find your equilibrium concentrations. Once we have our equilibrium concentrations, then we can calculate our pH. So my pH is the negative log of the concentration of hydronium at equilibrium. So the concentration is 1.9 times 10 to the negative third. So that's going to give me a pH of 2.71. 2 sig figs in my concentration, 2 decimal places in my answer. Now we're also asked to calculate the concentration of hydroxide. Hydroxide is always going to be present in our solutions, and we can calculate them based on our hydronium concentration. So again, we're using that equation that Kw equals the concentration of hydronium times hydroxide. I rearrange my equation because I'm looking for hydroxide. Hydroxide equals Kw over the hydronium concentration. Kw is 1 times 10 to the negative 14th. The hydroxide concentration was 1.9 times 10 to the negative third. So that's going to give us hydroxide of 5.3 times 10 to the negative 12th. The final thing that we're asked for is to calculate a percent dissociation. So in previous chapters, we calculated a percent reacted. And when we calculated that percent reacted, it was our change divided by our initial concentration times 100. We're doing the same thing here. We're looking at how our substances changed over our initial concentration. So my change is X, 1.9 times 10 to the negative third, divided by the initial concentration of 0.25, which is going to give me a percent dissociation of 0.76%. Now remember, with equilibrium problems, we check our work. We have a small k here. Small k means that I should have mostly reactant left over, very few product formed, which would correlate to small percentages. So my percent here, I have less than 1% of my acid dissociated. That is correlated to having a weak acid, a small k. So I should have small percents. In terms of my pH, my substance was an acid, we should have an acidic pH. Going back to my concentrations, in reference to K, I have small amounts of product. They're on the scale of 10 to the negative third. and I have mostly reactant left over. We've used very little of our reactant. So our answers make sense. When they don't make sense, that's our clue to go back and check our math. Now here we had looked at an example of a weak acid. If we've got a weak base, we're going to take the same approach. The difference is our proton transfer equation. So here we've got a 0.075 molar solution of CH3,3N, in which Kb is 6.5 times 10 to the negative fifth. Again, any problem, we want to know, is this an acid or a base? Is it strong or weak? I don't have a hydrogen out front. I don't have a COOH, so I can eliminate acid. I do have a nitrogen with 3 bonds. And if I have a nitrogen with 3 bonds, it's got a lone pair, so it can be a base. So this is a base. To be a strong base, it has to have a group 1 or group 2A cation attached to hydroxide. When there's no hydroxide, this is automatically a weak base. So we can write the proton transfer equation for this. So I'm going to take my base, I'm going to add it to water. Again, we're using the double arrows since it is weak. As a base, we're going to take a hydrogen from the water. So this becomes CH3,3, NH plus, and hydroxide. We've got an equilibrium, so again, we can represent that with a K. Because this is a base, that K is a Kb. So Kb will be equal to the concentration of CH3, NH plus times the hydroxide divided by my original base, so CH3,3N. Very similar to our previous problem, our ultimate goal is that we are looking for the pH. And in order to do that, we've got to get our equilibrium concentrations. So part E is asking us to set up our ice table and find those equilibrium concentrations. So setting up our ice table, we're going to plug in our initial concentration. We don't care about the water, and our products are initially 0. My reactant will go down by X. My products go up by X. So at equilibrium, my base is going to be 0.075 minus X. And then my conjugate acid will be X. My hydroxide will be X. So we've got to take that equilibrium line and plug it into our K expression. So I've got X for my conjugate acid. I have X for my hydroxide. X times X gives me X squared. On the bottom, I have my base concentration, which is 0.075 minus X. And that equals our K. We were told that Kb equals 6.5 times 10 to the negative fifth. Just like before, we're going to check for X negligibility. So we're going to take our K. We're going to divide it by our initial concentration. We will find that it is less than 10 to the negative third, so X is negligible. So again, with X being negligible, that means this minus X, we can drop. And when we drop that, my equation becomes X squared over 0.075 equaling 6.5 times 10 to the negative fifth. So again, I've got something that is much more easily rearranged. So anytime we're dealing with these weak substances, these small k's, we're going to check to see if X is negligible. It's not always, that's why we've got to check. But we can rearrange this. And we're going to find our X is 2.2 times 10 to the negative third. So we take that X, we plug it back into our ice table. So we're going to get, from our hydroxide, 0.002. For my conjugate acid, 0.0022. And then for my base, I've got 0.075 minus 0.0022. So that's going to leave me with 0.073. Checking do these numbers make sense. I have a small k. I should have most of my reactant left over, which I do, and very small amounts of product being formed. Now again, we're asked to calculate the pH. And so at this point is where we've got to be careful. We've got to pay attention to what we have. At this point, what I have is the concentration of hydroxide. So there's a couple of ways we could approach this. We can convert hydroxide concentration to hydronium, or we could take our pOH. And so I'm just going to go ahead and do the pOH. So that's going to be the negative log of 0.0022, so that my pOH is 2.66. And then my pH will be 14 minus that. So I have a pH of 11.34. We've identified this substance as being a base, so since it's a base, we expect a basic pH, which we have here. And then finally, we're asked to calculate the percent dissociation. So again, that percent is our change divided by our initial times 100. So the change is X. My initial concentration is 0.075. So we're getting a percent dissociation of 2.9%. So roughly only about 3% of my base is dissociating. I've got about 97% of that base still left over. So on your worksheet, you got problems 4 and 5 for additional practice. There's an answer key to these problems posted in Blackboard.